Hello everyone, let's take a look at our next problem. Find the volume obtained when the circle of radius 1 with center 1, 0 is rotated about the y-axis. Okay, so always helps to draw a figure when we have something like this. So if I call this the point 0, 1, that's going to be the center of our circle. I'm going to draw a rough circle like this. And then we are rotating this circle around the y-axis. And as we rotate the circle around the y-axis, it'll sweep out a solid shape. It's wait a minute. That's not the right point. I mean, I guess it doesn't matter, right? Because we're just going to have everything shifted straight downwards. And again, we're rotating around the y-axis, so the volume of the shape isn't going to change. So the solid shape that's going to be swept out here it's kind of a torus. It would be a torus if the radius of the circle were any smaller, or if this point were a little bit to the right. Like this, the point of the origin it's like a torus where the inner radius is 0. But how are we going to do this? Okay, so my first thought is let's think about a slice of this circle. So a piece of the circle like this, an infinitesimally thin rectangle. When that gets rotated around the y-axis, that's going to sweep out a shape of a hollow cylinder, and we can compute the infinitesimal volume of that cylinder, and then just integrate between the necessary bounds. Okay, so if we call this value x, if I call this x, then the height of this piece, h of x, well, I guess let's write out the formula for this circle first, shall we? So this circle is defined in terms of x minus 1 squared plus y squared is equal to 1. It'll help to rewrite this as y squared is equal to 1 minus x minus 1 squared. Okay, so the height of this cylinder, or basically the length of this yellow bar, is going to be 1 minus x minus 1 squared under square root times 2. Okay, so how did I get that? Well, if this is the value of x I'm concerned with, then the square root of this is the value of y up here. Well, the positive square root gives us that. It's symmetric for positive and negative values of y. And so the total length of that yellow strip is 2 times the distance between the x-axis and the top. So that's h of x. This strip is going to be rotated in a circle of radius x. So if we're rotating this yellow strip around the y-axis, this is the radius of the circle that it's being rotated about. It's being rotated around like that, where it's kind of coming out of the screen. So the area of one of our infinitely thin cylinders is going to be 2 pi x h of x, because if this distance here is the radius of the circle it's being rotated through, that has a distance of x, and so 2 pi x is the circumference that it gets rotated through, and h of x is the height, so the total area is like this. And so what is the final volume here? It's going to be integral as x goes from 0 to 2 pi x h of x dx. Now, I don't know if this is the best way to do this. This is using the cylindrical method. Cylindrical method of integration, but maybe it'll be helpful to do the shell method instead, or the disk method. I don't know what the names of these things are. I just like to picture the geometry. Is this going to be something easy to integrate? Oh, I'm missing a factor of 2 here from the h, so this should be a 4. 4 pi x times 1 minus x minus 1 squared under square root. Maybe this can be done, because I see if I'm going to expand what's under the square root here, and I notice that I'll end up with an x squared. And so a substitution might work, but there's also going to be an x. Let's see what happens when I expand this. I'm not sure I can come up with an easy way of doing this integral. I'm going to leave it here for now, and what I'm going to do is try and write out the volume using the other method for computing revolved or volumes of rotation, and see if we get a more straightforward expression. All right, so in this case, we want to think of this as being, when this gets revolved around the y-axis, we have an inner radius and an outer radius. So let's say that we have a fixed value. Let's say that we have a fixed value of y. I suppose maybe we'll want to write things in terms of x. Okay, so depending on whether I choose the positive sign or negative sign, that's going to give either the inner radius or outer radius of the shape that I'm interested in here. The variable y is always going to be between 1 and negative 1. So this term is always going to be positive, so there's nothing wrong with taking square roots. And the two values of x that I end up getting just give me either the inner or outer radius. Okay, so let's do it like this. The inner radius, this is 1 minus this expression. The outer radius is 1 plus this expression. The area as a function of y is going to be pi times the outer radius squared minus pi times the inner radius squared. I wonder if we're going to get some kind of cancellations here, but I am going to expand this. Okay, so I end up with pi's cancel, I end up with 4 pi times 1 minus y squared under a root. And the 1 minus y squared cancels in each case. So this is the area of our hollowed out disk as a function of y. And my volume in total, I'm going to want to integrate this as y goes from -1 to 1, a of y dy. This looks like it's a much more tractable form of the integral. Now it's just a case of trying to remember the appropriate substitution to make for this type of square root thing. It looks like something trigonometric, perhaps, right? So if I make this substitution, the integrand along with the differential turns into this. What are my bounds of integration going to be? Well, I want y to start at -1 and end at 1. So that's going to be negative pi over 2 to pi over 2, right? And now, now I'm going to use, there's some sort of, there's a something which allows me to reduce the power on cosine there. I can never remember these things, but nice way to figure out the identities is to just write out Euler's formula. Okay, if I identify the real and imaginary parts of this, I get cosine squared can be written in terms of cosine 2 theta. And so the integral that I need here is going to be 4 pi times this expression. I'll do a quick cancellation here. And this is essentially just a straightforward integral. So I'll go ahead and do this without comments and hope that I don't make any arithmetic mistakes. So this is the final volume I get, 2 pi squared. I was a little bit, perhaps a little bit surprised to see this second term not end up contributing anything, but I mean, that's, I suppose that's just how it goes. Yeah, and I wonder how much different this problem would be if the circle didn't intersect the origin here, right? So that would change, I suppose that would just change this number, which ends up changing that number. I'm sure it's not terribly different overall. Just another, it looks like there's just going to be another scaling factor or something like that in here. But yeah, this was a good problem. I liked, you know, it really just goes to show that the two different methods of computing these rotated volumes really can end up, you know, one really can give you a better approach than the other. I wouldn't know where to start in trying to integrate something like that by hand, which is why I stopped there right away to try and develop the other method. Thanks for watching.